We have Nikolaos Zygouras from University of Warwick about intermediate disorders with the critical stochastic flow.
Okay, thanks, Daniel. Thanks, everybody, for staying, and thanks for inviting me here. It's a great honor to participate in this celebration of the contributions of Jeremy and the influence he had on the field. And so actually, the title of my talk would also have been the intertwining between my work and the work of Jeremy and his collaborators. So haven't collaborated with Jeremy, but his work has definitely been influential to me. And so from this perspective, it has been a fruitful collaboration. So let me start. Let me start by discussing what is the intermediate disorder regime, which was introduced by Alberts-Khanin-Quastel with the purpose of introducing an approximation to the stochastic heat equation or to the KPZ equation through the random polymer model. So very quickly, the random polymer model has this function. Has this partition function. So everywhere on the space-time lattice, you have an independent random variable omega, and you also have a random walk Sn, which runs on the points of the lattice, and collects in the energy all the omegas traced by the random walk. So here you have the expectation of this with respect to this random walk starting at x, and the conditioning to ending up at y. So beta equal 0 basically corresponds to the simple random walk. Beta equal infinity corresponds to last pass at percolation. And the in-between values of beta is interpolation between extreme last pass at percolation, extreme optimization problem, and extreme entropy problem. The high temperature goes and prompts what happens very close to beta equals 0. So you scale beta by n to the negative gamma, and you ask a particular value of gamma for which the partition function Zn with temperature Bn has a non-trivial limit. So Alberts-Khanin-Quastel established that when gamma is equal to a negative quarter, then the limit of the partition function converges in distribution to the solution of the stochastic heat equation. Maybe. Okay. So, and this happens for every beta hat. So you have beta hat being the parameter in front of n to the negative quarter. So the standard assumption in direct polymers is that the moments have exponential, the distribution of omega has exponential moments, but in the paper of Alberts-Khanin-Quastel, it was also conjectured that the same intermediate disorder scaling limit should hold for having 6 moments. And that was one of the first inspirations. So I looked that I had. So I looked at this problem with parts a day, and yes.
What's the scale? How is the space we scale?
The space will be the scale. The space will be squared. Yes. Okay. So with parts a day, with at Urbana-Champaign, and at that time he was at Warwick. We looked at this question and were able to establish that the intermediate disorder regime is still valid when you have alpha moments, 6 moments for omega. And actually, we were able to propose a more general diagram, phase diagram. So on the vertical axis, we have how many moments the disorder has. So alpha corresponds to the tail of the disorder. And on the vertical axis, we plot gamma, which is the exponent of the intermediate disorder scaling. So if you go in the upper left corner, when gamma equals 0 and alpha equal infinity, you are in the KPZ universality class, and you have fluctuations, spatial fluctuations to two-thirds. In the other black bullet on the top, this corresponds to the Alberts-Khanin-Quastel intermediate disorder regime. And, so this doesn't work. And so this line here, scale the disorder by n to the negative quarter. And okay, all right, it's okay. So, and you go up to 6 moments. But something also interesting here, you have fluctuations square root n. So you have a special exponent 1/2. So in the paper of Alberts-Khanin-Quastel, we was also conjecture that the intermediate disorder regime, so when you go up to here, so the exponent gamma should interpolate linearly between 0 and 1/4. And that was established, that was proved for the O'Connell-Gord polymer by Timo, Benedek-Valko, and Gregorio Moreno. So what we have in this diagram? So, okay, so this line here is the intermediate disorder regime n to the negative quarter with special fluctuations square root n. But with Partha-Day, we also went below 6 moments. And then if you follow this curvilinear line, then you will still have special exponent 1/2. So between alpha equal infinity and alpha equal 6, you converge to the stochastic heat equation, but there is difference in distribution, in the distributional limit when you go below alpha equals 6. So if you come down along this line from alpha equals 6 to alpha equal 2, then you will have Gaussian fluctuations. And below alpha equal 2, you start picking up Poissonian fluctuations. So what else is known about this diagram? So another thing that is known is this black line here and what happens below. And this is what I will call Aufinger-Lütke line. So, right, but okay, what are these lines here? So each line, so if you pick an exponent psi and you ask what is the line in the alpha gamma phase diagram that has a special exponent psi, this will roughly go as follows. So you will start from infinite moments, and then you will go down as a straight line. And then you will, when you go down to the red line, you will follow a curved line. In particular, this line here that starts for gamma equals 0 and goes down in this way corresponds to fluctuation, should correspond to fluctuation exponent 1/3. So you should be having KPZ fluctuation exponents. Maybe different distributions, but the fluctuation exponent should be 1/3. So most of the part of this diagram is still conjectural. One thing that is known is what happens for alpha below 2 and still in the red regime. In the work with Partha-Day, we stated a conjecture that the fluctuations should have a certain exponent and a certain distributional limit, which is given in terms of entropy energy optimization problem. And this conjecture was established by Tamperger and Nikolaos Zygouras. But everything else in this diagram is still conjectural, and I think it's an interesting direction to investigate. Okay, but the main actually influence that the intermediate disorder regime had in my work was when with Francesco and Ron Frank, we were looking at some disordered models, and then we thought that maybe having scaling limits through an intermediate disorder scaling would be useful. And actually, we're able to connect it to what's called in statistical mechanics and disorder systems the Harris criterion. So let me start by saying what is a disordered system. So a disordered system is a mixture of a pure statistical mechanics model and some disordered omega. So you have the lattice on RD, on ZD, with a mesh delta. Every side of the lattice carries a pure random variable, which can be a spin random variable or an occupation random variable. And also it carries an independent disorder, omega. So the two things come together and they produce the disordered measure, which is a tilting, a Gibbsian tilting of the pure statistical mechanics method. This is very similar to the Gibbsian tilting that we have in direct polymer model. Okay, so the question of interest in disordered system is whether arbitrarily small amount of disorder is able to change the statistical mechanics properties of the system. If it does, this is called disordered relevance. If it doesn't, it's called disordered irrelevance. And in 1974, there was a criterion proposed by Harris, which is known as the Harris criterion, which says that the disorder is relevant if the fluctuation exponent nu of the pure system is strictly less than 2 over d, 2 over the dimension. So in the first work with Francesco Caravana and Ron Feng-Sun, we were actually able to we proposed an alternative formulation for what is disorder relevant. And the formulation we gave was that disorder is relevant if you can find an intermediate disorder scaling of the model, such that as the mesh goes to 0, you compare it with a non-trivial and random object. Actually, it was very surprising to see that the intermediate disorder scaling is actually equivalent to the Harris criterion. So if the Harris criterion is valid, then you can find the exponents alpha and b, a and b here, such that you have a non-trivial intermediate disorder scaling limit. Okay. A more interesting question is what happens when nu is equal to 2 over d. In this case, is called the marginal case, and this is the most subtle case. And when you are at nu equal to 2 over d, then you can either be marginally relevant or marginally irrelevant. And then one needs to look very close, much closer into the system to decide. Actually, this notion of marginal relevance or disorder relevance turns out to be equivalent to what in SPDs or in normalization theory is called criticality. And so criticality in SPDs is actually equivalent to marginality. And, just to give you an idea how this works, let me look at the stochastic heat equation, which is the object up there. And let's make a renormalization transfer. So we look at the solution when we scale space and time in a parabolic way. And then we ask, what equation does this rescaled solution solve? So if you use the scaling properties of the white noise, it turns out that U epsilon solves this equation with a factor epsilon to the d minus 2 over 2 in front of the noise. So when d is less than 2, so in the stochastic heat equation, the critical dimension turns out to be 2. And when d is strictly less than 2, so it's 1, then the strength of the noise becomes much more and more prominent. So the noise will dominate. And then you have disorder relevance. If d is greater or equal to 3, so the noise is attenuated. So gradually, you don't see any effect of the noise. But if you are at dimension d equal 2, the exponent vanishes. So you cannot see whether the noise has an obviously dominant effect or an obviously negligible effect. And then you need to start looking much more carefully. Okay, so a first result we prove with Francesco and in this direction is the following. So let's look at the partition function of a marginally relevant model of directed type. So it can be a two-dimensional directed polymer model. It can be the two-dimensional stochastic heat equation. It could be one-dimensional random walk with long jumps in the Cauchy domain of attraction, and pinning models and others. And what we saw is that the intermediate disorder scaling in dimension 2 takes logarithmic form. So the n to the negative quarter in dimension 1 should be replaced by 1 over square root log n. And when you look at the limit of the 1-point distribution, so you fix, let's say, the starting point of your random walk. And for this fixed initial point, you ask what is the limiting distribution of the partition function. So it turns out that there is a phase transition in this beta hat. So if beta hat is strictly less than 1, then you converge to a log normal distribution with an explicit variance, which actually blows up when the parameter beta hat hits the critical value 1. And when beta hat is greater than or equal to 1, then you converge to 0. So somehow this is quite much analogous to the picture known in direct polymer models, that you have weak and strong disorder. Only what was proposed is that in direct polymers, you should have a phase transition only in dimension d greater than or equal to 3. What actually we showed here is that in dimension 2, you still have a phase transition, but you need to look much closer to beta, to the region of beta, the neighborhood of beta equals 0. In dimension 1, there is no phase transition. So for any beta equal beta hat times 10 to the negative quarter, you will always converge to the stochastic heat equation. Okay. This 0 is not really satisfactory, and that will be something to discuss later. A second type of result that we have is what happens at the fluctuations of the field. So you look at all partition functions for all random walks starting at different points, and you want to ask how these are correlated. So what we saw is that if you set the field by 1 actually you should think as a solution of the heat equation, and you rescale by square root again, then you converge to the Gaussian free field. And the Gaussian free field, you can also think of it as the solution to this additive stochastic equation. And again, one thing that you observe is that the strength of the noise becomes infinite when you hit the critical value beta hat equal 1.
The factor 1 over 1 minus beta squared looks like a geometric factor.
Yes.
Of the variance. So is this related to the fact that like you do the chaos series and you only keep track of kind of finite chaoses, you won't get that factor?
Okay, so that's one thing that so in this case they don't run to infinity, but the difference between critical and subcritical dimensions is that at critical dimensions, basically all the terms in the chaos expansion contribute. When you are below the critical temperature, beta hat strictly less than 1, then the contribution of each chaos decays in a geometric way. The interesting thing happens when you hit beta hat equal 1, that actually the main contribution moves at the higher order terms of the chaos. Right, so before discussing the case beta hat equal 1, I want to mention a few other works that have been studied in mostly nonlinear stochastic partial differential equations at the critical dimension. So the first one was a KPZ equation. So again, you can attenuate the noise by 1 over square root log epsilon, and then the solution will also have, when you are below the critical temperature, will have again Gaussian free field fluctuations. So first result in this direction was by Chatterjee and Dunlap, who showed the tightness of the field. And actually, this result motivated us to show that in the whole subcritical regime, you have Gaussian free field fluctuations. And a couple of weeks later, Zygouras essentially put out the same result. I guess we were working in parallel on the two sides of the Atlantic without knowing about it. And yeah, I think I should apologize to Zygouras for rushing him, but I think it's also better to have two papers than none. That's what they say. So, okay. Second is anisotropic KPZ, two-dimensional anisotropic KPZ, and this is a program that has been initiated recently, has lots of activity by Giuseppe Cannizzaro, who is also at Warwick, initially with Dirk Erhardt and Sean Bauer, but also now Fabio Toninelli is very interested into this, and Massimiliano Rubinelli. And here they use a different set of methods, actually going back to the works of Yao on the two-dimensional asymmetric exclusion process. I should mention one difference between the isotropic KPZ and the anisotropic KPZ. So in both cases, you do the same scaling. So you scale, actually you can scale either the noise or the nonlinearity by a constant divide by square root log epsilon. These two things are equivalent. And in the two-dimensional KPZ equation, there is a phase transition where you change from the Gaussian free field to something else that we don't know yet. But in the anisotropic KPZ, you don't have a phase transition when you change the strength of the 1 over square root log epsilon. Okay, other very nice works is by a series of works by Dunlap, Gu, Graham, Rantau on the semi-linear stochastic heat equation, where they get some very interesting limits. So instead of a log normal distribution, the limit of the one-point function is given in terms of a forward-backwards stochastic differential equation. And more recently, Simon Gabriel and Tommaso Rosati, we looked at the Allen-Kahn equations, where here was the motivation was to look at some nonlinear model without doing any linearization. And then we start seeing structures, tree structures like what appears in regularity structures. Okay, but all these results are confined in the two dimension, at critical dimension, but they are confined below a critical temperature. And now I would like to pass to the critical temperature. And this is the result we have with Francesco and Renfeng. So if you have beta hat equal 1, and then you can allow a lower order window around 1, then the solution of the partition function of the two-dimensional directed polymer, when centered by 1, but without any rescaling. So when you hit the critical temperature, is the moment where you start seeing strong correlations. So you don't need to blow up your field to see the correlations. Then you have a unique limit, which we call the critical two-dimensional stochastic heat flow. So we know some things about this object. We know that it's a low correlated field. It's kind of obvious that it's not a Gaussian because it's a positive. It has to be a positive field. But it's much less obvious that it's not the exponential of a Gaussian field. So it's not a Gaussian multiplicative chaos of any sort. We also know that it's a measure. So another thing that happens when you are in 2 dimensions and at the critical temperature, you change from random functions to random measures. So now the solution to the stochastic equation or the limit of the direct polymer will become a random measure. And this random measure becomes singular with respect to the Lebesgue. And there are some aspects of self-similarity of this model. For example, if you do a space-time scaling, parabolic scaling of the points of the, yes, if you do a space-time parabolic scaling and you look at the field in this space-time parabolic scaling, you will get the same limit, but with the theta, which appears here, shifted by a log of the scaling. Okay, so we know some aspects, some features of this model, of this object, but there are many things that we should know. So how does it look like? So, okay, so it may look like a Bryce Canyon. So this is a simulation when you have flat initial condition, and you go. I went up to 64,000 steps. So, or if you start with a delta initial condition, it can look like this picture. So this is somewhere in the middle of Greece. It's called Meteora because it's like meteors. Okay. Or it can look like Dubai. But in all these pictures that you see, in all these pictures, what you see is that you see kind of accumulation. You see patches somewhere. So these patches actually may move around. It may become kind of sparse, or it may become kind of extended, which is something that I don't understand why sometimes they look sparse, sometimes they look extended. It's a method, but it's singular with respect to Lebesgue, so it concentrates in patches, but putting needles somewhere densely in these patches. Yeah, time. Yeah, here is time actually is a bit less than the previous slide. It's also something to be understood, but actually, nature built this structure took more time than humankind building this structure. You can see it in this way. Yes, Pierre?
Did you check if there was some multi-factor exponents?
Sorry?
Did you look for multi-factor exponents?
Well, this no, but this is something that it will be one of the questions that will appear at the end. Yes, that's something in the program. Yeah. Another thing that we need to look is what happens with the log of it. So the log should be a kind of a critical two-dimensional KPZ equation. And yeah, okay. So this is a confirmation, I think, experimental confirmation. Okay, how much time do I have? 15. Okay, good. So I'll be able to say some, to touch a bit, to describe a bit the structures that appear and the methods. There's a difference between the structure, the underlying structure, if you are below the critical temperature and at the critical temperature, and also the methods that we use in the two cases. But I will only be able to discuss what happens at the critical temperature. Okay, so our starting point to analyze this model is the chaos expansion. You can think of chaos expansion if you come from SPDs by just doing the Picard iteration. So the Duhamel's formula. So if you repeat the Duhamel's formula, you get some series, some chaos series. But if you come from statistical mechanics, you want to do a high temperature expansion. So you expand the exponential. And what you get eventually is a representation of the partition function as follows. So you pick k space-time points, where this will be the only points where your walk will sample the disorder. So your walk will jump in between these points, and the weight, the probability of jumping in between these points is q and x. So you look at all possible combinations of the number of points k that you pick, that you sample, and where are the space-time location of these points. At the critical temperature, we proceed by doing coarse graining. So again, this will also see that it has a sense of renormalization. So we split the space-time domain into boxes of time increment epsilon, time length epsilon n, and diffusive width. And then we ask, okay, which blocks are sampled? So which are the blocks that the walk is going to visit and sample noise? And in fact, actually, if you look from very far away, I think probably you guys in the back, you don't see much difference between the two pixels, right? So both of them look like dots and something jumping in between. And the idea is actually we want to take a large n limit, and then the idea is to say, okay, all the let's say all the fluctuations are in this box in these boxes. So let's in the large n limit, maybe I can take this box and replace it by just an independent Gaussian random variable in the large n limit. So in the large n limit, what you will be seeing here is again a polymer of length now 1 over epsilon. Now we change from the microscopic length scale n to the mesoscopic or macroscopic scale 1 over epsilon. So if I were able to take this box of disorder, of complicated disorder, and take it away, throw it away, and replace it by some Gaussian, then basically I'm seeing the same model. So this is also the self-similarity I was talking about. So somehow maybe we can take the large n limit by doing this. And this is actually something that is also familiar in classical probability. This has the spirit of a Lindeberg principle. So if you want to look at the central limit theorem, there is one distribution for which the central limit theorem is trivial. This is the Gaussian. If you have other distributions, then you want to start replacing the general distribution by Gaussian 1 by 1. Okay, so what do you need to do in order to apply this Lindeberg principle? So Lindeberg principle holds with, you need to have first matching and second moment, matching first and second moment. And you also need some control of higher moments, let's say fourth moment, so that fourth moment will guarantee, if you have finite fourth moment, it will guarantee that the error that you make by taking the complicated disorder and replacing it by some Gaussian is negligible in the large n limit. Okay, so first moment is 0, that's okay. What about the second moment? So here is where the interesting aspect comes in the critical temperature. So if we compute the variance of this partition function in this coarse-grained block, then we see that it has the same logarithmic scaling like the original microscopic disorder omega, but most critically, most crucially, the parameter beta that multiplies the log is again critical. So by this renormalization, basically you don't change. If you replace the disorder, the coarse-grained disorder by some Gaussian, what you will be putting in will be again a critically scaled disorder. So the model is basically invariant. So this renormalization transfer doesn't change. It doesn't bring you down to something trivial or something blowing up. So this having precise estimates about the variances has been very important. And actually, we're able to get these precise estimates by linking to some Levy theory. In fact, actually, we could compute that the variance is given by basically the Green's function of some distribution, which initially we called the zero-stable Levy process, because the tails is like alpha equals 0 in Levy processes. And then when we put out the preprint, the next day we received an email by Thomas Simon saying, okay, this function, one thing that was interesting, that we compute exactly the density of this subordinate. This density is known since 1930s, and actually it's called Dickman function. It's very important in analytic number theory or in the random permutations. So from then on, we call it the Dickman subordinator. Okay. So we could control the first and the second moment, but then in order to put forward the Lindeberg principle, we needed to have higher moments. And we had written a very long paper, quite complicated as well, controlling the third moment, but actually that was not quite good enough, because you would like some absolute value, not just the third moment. fourth moment would have been good, but then, right, so it was getting complicated. So you can relate the fourth moment of a polymer model to exponential moment of collisions times of a system of independent random walks. So the fourth moment of the partition function, you can also picture it as the exponential moment of 4 independent random walks, starting at different locations and then colliding. And you want to show that this is also related to delta Bose-Gas. So you want to show that this delta Bose-Gas, this system, this exponential moment is finite. So this diagram is complicated. For 3 particles, we were able to do it, but then we were also tired, and it was also getting quite complicated to track the 4 particles. But then there was this also important paper by Zygouras and Tsai. What they did is they put the lines here. So I think I also, yeah, so these were also related to works in mathematical physics, I think by Dimok and Rajev. So the mathematical physics, they were interested in delta Bose-Gas and defining self-adjoint extensions and so on. And yeah, another work also was useful, I think, for the Zygouras and Tsai was Del Antonio, Figari, and Theta. So that was 94, and that was, I think, maybe 2004 or something. So putting these lines was a very good trick because it allowed actually to break this complicated collision diagram to a Markovian structure. Right. So yeah, the lines means that I basically I will be looking at the Markov. You'll be using the Markov property. So you see how much collision is from here to here, okay, and then essentially how much collision, what's the contribution here. So it's like Feynman-Katz formula. It's a semi-group property, basically. Okay. So this diagram is difficult because it's convoluted. Okay. But we can go to the resolvent and basically write this convoluted diagram as a geometric series. And the geometric series will have 2 components. One is what we call the collision solution. So how much local times you have picked by 2 walks colliding. And the other is the free evolution. So the one on the top, we were able to do it. We had already done it using the Dickman subordinator. But the second evolution is also quite tricky. Because basically, if the first point and the second point come together, then the diagram will blow up like the same way the 2-dimensional Green's function will blow up. Okay, so maybe I will not go too much into the details of this, but one thing that was important for us to control the second diagram was to establish a critical Hartley-Littlewood-Sobolev inequality. That was an inequality already used in the Zygouras-Tsai paper, and originally it was a paper of Del Antonio, Figari, and Theta, but it was in the L2 sense. In order to apply the Lindenberg principle, where we are interested about the influence of every point, so we had to extend this to LP and LQ spaces. So yeah, we devised a different proof, which it worked on the real space rather than on the Fourier transform, and also was good for discrete settings and also in general LPs and LQs. Okay, so this is a bit technical part, but let me just try to wrap up with some questions. So, Okay, so we have this construction of this object, this unique object. We know some of its properties. We have seen some pictures of it, but there are many things that we need to want to understand. So one of it is, can we have an axiomatic characterization of this object? So if I give you, if I give you the one-time marginal, can we have an axiomatic characterization of this measure analogous to what exists for the Gaussian free field? So for example, the Gaussian free field is a unique Gaussian field which has low correlations and the domain Markov property. So does something like this exist for the pictures I showed you? And this will also be useful in order to extend the universality. So our results have some sense of universality in the sense that we don't care what is the distribution of the omegas. We don't need to restrict to particular distributions, but can we extend beyond, in an easy way, beyond direct polymer models? So what are the relations of this model? So this is a two-dimensional geometry to other two-dimensional geometries like Gaussian multiplicative chaos, revealed quantum gravity, and so on. Understand the questions about the spectrum, like what Pierre asked, the fractality of the measure, the structure of the thick points, what's the regularity of the measure, and so on. There are some still interesting questions about the delta Bose gas and the asymptotic. So if you have, let's say, the pith moment, how does the pith moment grow? And whether actually this can tell us some information about the statistics of the stochastic heat flow. Okay, and eventually, yes, it would be really great if we can, now we have a theory of SPDEs below the critical dimension, but can we also push forward for a theory of critical SPDEs? And this can be summarized like in the following. So in the upper left corner, you see a simulation of the critical 2D stochastic heat flow. Below, you see two different realizations of the Gaussian multiplicative chaos coming from different models. And here you see a revealed quantum gravity. On the right, on the top, you see what should be a picture of the logarithm of the stochastic heat flow or the two-dimensional critical KPZ equation. Below, you see a picture of the Gaussian free field. So what would be really nice is the following. So if I give you, can we develop a methodology so that if I give you two of these pictures, you can tell me which one is what. Okay, and with this, I would like to stop. Thank you, and happy birthday, Jeremy, and keep giving us inspiration.
I just have a naive question. The simulation on the top left corner doesn't look as symmetric if you swap that x1.
Sorry, it doesn't look like?
It doesn't look that symmetric if you switch x and y.
Yeah, so this is, I mean, the statistics, the distribution should be, yes, invariant under these kind of switches. But this is one realization. Yes, so it happened that, in this realization, the peak moved in that direction. Yes, this is the kind of semi-extended, right? So it's not really sparse. Yeah, I think it's just because of it just happened with the simulation, the particular simulation.
Any other question?
Yes.
So, you mentioned that you have some expression on the moment, and you also mentioned about the asymptotic of the moment growth. So, is that hard to?
Yeah. So, for the moment, we have upper and lower bounds. So, the pith moment, the lower bound is e to the p squared. The upper bound is e to the p squared. And in this paper of Dimok and Rajev, and in particular in the earlier paper of Rajev, there is some conjecture, looking at Bogolyubov theory, that the growth could be e to the p. And actually, this would be interesting to compare in dimension 1, the delta Bose gas has growth e to the p to the q, to the e to the p to the 3. And now this also raises a question, in dimension 1, Kardar used this to say that the fluctuation exponent is t to the 1/3. What can we extract by knowing the asymptotic of the moments? So that's not clear. Yes.
Perhaps we could thank Daniel and Ivan for putting together such a wonderful celebration of Jeremy's work.
Okay, I was supposed to do
So in a second, we're gonna thank Nikos again, but don't leave right after because. Yeah. Okay. So Jeremy was gonna. Anyway, then maybe let's thank Nikos. Right, well, the speakers. Thanks very much for being here. I think it's been great to see so many people around every day. So hopefully there will be much more to come.
Did you remember to thank Evan and Jean? Well, at least I did something.
And the building is open, so hang out. We're going home. Okay.